Hi, in this video I will show you some techniques for producing your own homemade power series. Let's first have a look at the power series 1 plus x squared plus x cubed plus x to the power 4 plus etc. In other words, the series sum n from 0 to infinity of x to the power n. You may recognize this as a geometric series, which is convergent if and only if x is between -1 and +1. And for these values of x, the sum of our series is equal to 1 over 1 minus x. Since this series depends on x, it can be regarded as a function of x. In particular, each partial sum is a function of x. Let's have a look at some of them. We have S1 is 1 plus x, so the graph of S1 is a straight line. Next we have S2 is 1 plus x squared, so its graph is a parabola. Then S3 is 1 plus x squared plus x cubed. And here you can see its graph. And so on and so forth. Now look at the behavior of these graphs. Between -1 and 1, they seem to stabilize. But outside this interval, they become quite nervous. How do we explain this behavior? Well, in fact, we just noticed that these partial sums converge if x is between -1 and 1. And if x is not between -1 and 1, there is no convergence. Moreover, if they converge, we know that the limit is equal to 1 over 1 minus x. So, let's have a look at the graph of S6 and compare it to the graph of 1 over 1 minus x on the interval from -1 to 1. As expected, the difference between these two functions is quite small. So, S6 can be regarded as an approximation of the function 1 over 1 minus x. In general, if a given function is equal to the sum of a power series, we can use the partial sums of the power series to approximate f. And since the partial sums of a power series are polynomials, they are very easy to compute. So the question is, if we have a function, can we find a power series that converges to our function? Let's look at some examples. Our first example is the function 1 over 1 plus 3x. So, can we find a power series that converges to this function? Well, simply take the previous example and replace x by minus 3x. This leads to the power series sum for n from 0 to infinity of minus 3 to the power n times x to the power n. And for convergence, minus 3x must be between -1 and 1. Which implies that x must be between -1/3 and +1/3 in order to make the series converge. So, if we take a partial sum of this series, for example S6, on the interval from -1/3 to +1/3, we have a polynomial approximation of our function. Look at this graph and see how it is being approximated by S6. And if you want a better polynomial approximation, simply take a higher partial sum. Here's another example, the function 1 over 5 minus x. By factorizing the denominator, we can write our function in the form 1 over 5 times 1 over 1 minus x over 5. In the same way as we did before, we find a power series for this function. We get 1 over 5 times the sum for n from 0 to infinity of 1 over 5 to the power n times x to the power n, which can be rewritten as sum for n from 0 to infinity of 1 over 5 to the power n plus 1 times x to the power n. For the series to be convergent, 1 over 5 times x must be between -1 and +1. So x must be between -5 and 5. Have a look at the graphs to see how S6 is doing. Not bad, is it? And we know that as long as we take x between -5 and 5, higher partial sums will do even better. But there's another way to regard 1 over 5 minus x as the sum of a geometric series. Simply write the denominator as 1 minus x minus 4. And then observe that this is equal to the sum for n from 0 to infinity of x minus 4 to the power n. Provided, of course, that x minus 4 is between -1 and 1. In other words, x is between 3 and 5. So the partial sums of these power series approximate our function on the interval from 3 to 5. Note that the approximation works best if x is not too far from the center of this interval, which is 4. Now suppose we want to have good approximation near some other point rather than 4. For example, let's say we want two polynomials that give a good approximation for 1 over 5 minus x for values of x that are close to 3. Then we need a power series that is centered at 3. In order to find this power series, we first write 1 over 5 minus x in the form 1 over 2 minus x minus 3, and then by taking a factor 2 out of the denominator, we see that our function is equal to a half times 1 over 1 minus x minus 3 over 2. This leads to the series sum for n from 0 to infinity of 1 over 2 to the power n plus 1 times x minus 3 to the power n. For convergence, x minus 3 over 2 must be between minus 1 and plus 1. So x must be between 1 and 5. Indeed, since the center of the interval of convergence is 3, we now have a power series whose partial sums are close to our function if x is close to 3. So far, we have been looking at functions for which a power series could be found by making use of the geometric series. However, there are many functions, for example logarithmic functions, for which we cannot directly use the geometric series. In class, you will learn about differentiation and integration of power series, and that will enable you to create power series for logarithms, for the arctangent, and for many other important functions. So, see you in class.